is called the original LPP, which is given is called primal. It's called primal LPP, which is called primal. Every LPP which is given is called the primal. Every LPP is associated to a uniquely related to another LPP involving the same data, uh, as described in the original LPP. The original LPP is known as primal, but the same LPP can be solved by the taking the transpose. We get the new LPP without changing the data. This newly formed LPP is called the dual of the primal problem. If the primal is a maximization problem, uh, then dual, its dual will be a minimization problem and vice versa. We shall study the concepts related primal and dual LPP in detail uh, in this present unit. Present unit. So page number 93. Page number 93. Hmm? 7.2. Formulation of dual linear programming problem. Let the given LPP uh, is the form maximize uh, maximize zx equal to c1 x1 plus c2 x2 so plus cn xn subject to constraints you are a1n xn less than or equal to p1 a21 x1 plus a22 x2 plus a23 x3 plus so on a2n xn less than or equal to b2 so on means it is continuous am1 x1 plus am x2 plus an1 x3 plus so on bn where x1 comma x2 etc xn greater than or equal to 0 greater than or equal to 0 can be represented in matrix formation as maximize z equal to cx subject ax less than or equal to b and x greater than or equal to 0 b transpose belongs to r power n say a11 a12 etc a11 1n second row a21 a22 etc an here a equal to am1 am2 etc amn x equal to x1 x2 etc xn b equal to b1 b2 etc bn here and c equal to c1 c2 etc cn so important points in formulation the dual of a primal problem. Okay, first point, what is that in a primal problem? If there are n variables and m constraints, then it's dual problem. A dual problem will have m variables and n constants. If the primal has less than, it will become greater than or greater than or equal type of constraints and vice versa. Vice versa. What is the third one? The third one. If the primal has the objective function as maximization function, then the dual has the objective function as minimization function. Minimization. Fourth one. The cause of the objective function in a primal problem will become as constraints in the dual problem, and the constraints of the primal problem will become cause of the objective objective function in the dual problem. The decision variables in both the primal and means all positive values. That means so. Thus, the dual of the above problem of one can be denoted by minimize z of y equal to b1 by 1 plus b2 by 2 plus so on bm by n subject a11 by 1 plus a21 by 2 plus so on plus am1 by 1 greater than or equal to c1 greater than or equal to c1. So a12 by 1 a11 by 1 am1 by 1 greater than or equal to c1. Similarly a12 by 1 plus a22 by 2 so on plus am2 by 2 greater than or equal to c2 so on a1n by 1 plus a2n by 2 plus so on amn by m greater than or equal to cn and y y greater than or equal to 0 I equal to 1 to m 1 to m. So is general we denote the problem phenomenon as a primal problem, dual problem. In primal, what is there? Suppose max zx equal to j equal to 1 to n cj into j such that uh, so in dual what we write suppose primal problem max z writing means in dual min z means minimization z of y equal to j equal to 1 to n bi yi such that j equal to 1 to n ij xj less than or equal to bj for j equal to 1 to n aij yj less than or equal to c1 j equal to 1 to n uh, where I equal to 1 to m. Suppose and xj greater than or equal to 0, j equal to 1 comma 2 comma etc. n. So in j equal to 1 to n, aij yj less than or equal to ci, where j equal to 1 comma 2 comma etc. n. n. And yj greater than or equal to 0, I equal to 1 comma 2 comma m. So some standard theorems on the marks. Most important for theory 10 marks question. Theorem. What is the theorem statement? Theorem. The dual of a primal problem is the primal. What is that? Once again, we'll read them. Theorem. The dual of a primal problem, dual of a primal problem, uh, the dual of a primal uh, problem is primal proof. How to read proof? Consider the primal problem. The primal problem is the canonical form. Min z equal to Cx subject to constant Ax greater than or equal to B such that x greater than or equal to 0 where A is a m cross n coefficient matrix and B transpose belongs to e power m theta. So Cx whole transpose belongs to e power m. On applying the rules of the dual problem, we get max zy equal to B transpose. Max zy equal to B transpose Y. Subject, A transpose Y less than or equal to C transpose. Y greater than or equal to 0. Let us express the primal in the standard form. So zy star equal to minus B whole transpose Y subject to minus A transpose Y greater than or equal to minus C transpose and Y greater than or equal to 0, where zy star equal to minus zy. Now the dual of the above expression is maximize z star that equal to minus ct whole transpose x equal to cx subject to minus A transpose whole transpose x less than or equal to minus B transpose whole transpose. That is Ax greater than or equal to B, which is primal. Remark. What is the remark? If the ith constraints in the primal problem, nth constraint in the primal problem has equality sign, uh, then ith dual variable is unrestricted sign. Unrestricted sign. Uh, Second remark. What is the second remark here? That the primal problem or the dual problem has an unbounded solution. Unbounded solution. Then other problems has feasible solution. Other problem is a feasible solution. So fundamental theorem of duality. This is also most important for 10 marks theory. Fundamental theorem. Statement. If the primal or the dual has a finite optimum solutions, then the other problem will also possess a finite optimum solution and the optimum values of the objective function uh, of either problem are same. The statement is, once again we read statement, if the primal or the dual, the primal or dual will has a finite optimum solution, uh, then the other problem will also possess a finite optimum solution and the optimum values of the objective function of either problem are the same. Same. Next theorem. Huh? Next theorem, page number 96. Theorem, complementary slackness theorem. Complementary slackness theorem. If x and y are the feasible solutions to the primal and the dual uh, problems respectively, then the necessary and a sufficient condition for X star and Y star be the optimal solution, to the respective problem is that uh, yi xn plus 1 equal to 0, uh, I equal to 1 to m, and xj ym plus j equal to 0, j equal to 1 to etc. n. Hmm? X I plus 1 is the ith slack variable in the primal LPP, and y m plus j is the jth surplus variable uh, for dual LPP or dual LPP. Note, the proof of above theorem will be given in higher classes. Okay. So duality and simplex method. Duality and simplex method. So duality. Duality and simplex method. A simplex method can be applicable to both primal as well as to dual LPP. As any LPP uh, can be solved. Namaste. Um, yeah, but duality and simplex method. So simplex method uh, can be applicable to both the primal as well as dual LPP. Dual LPP, as any LPP can be solved using simplex method from the fundamental theorem of duality. We have an optimum solution associated to the dual can be obtained from the primal and vice versa. So remarks on primal and dual optimum solutions. Dual optimum solutions. So first way, if the primal or dual variables corresponding to the slack variables in the dual primal problem, its optimum value is directly read off from the dual or primal simplex table uh, as the primal simplex table as the as the examination the evolution delta j corresponding to that slack variables as to if the primal or dual variables corresponding to the corresponding correct, corresponding to that slack variables. Uh, in one of slack variables means slack variables, surplus variables, and artificial variables. Uh, so if the primal or dual variables corresponding to the official variables, the dual uh, primal problems, its optimum value is directly read off from the optimum dual or simplex, primal simplex table. Hmm, as the net evolution delta j corresponding to that artificial variable uh, after deleting uh, that constant. Write the dual of the primal. Example problem. Page number 96. Example problem. Write the dual of the problem. Dual of the problem. Uh, Dual of the maximize z equal to 4x1 for short answer type question. 5 marks questions. 5 marks question, most important. Uh, Write the dual of the problem of the primal. Max z equal to 4x1 plus 2x2 4x1 plus 2x2. Uh, so subject to constant minus x1 minus x2 less than or equal to minus 3. So minus x2 plus x2 greater than or equal to minus 2. And x2, x1 comma x2 is greater than or equal to 0. Uh, Solution. Solution is the standard form of the given LPP. Means linear programming problem is uh, maximize z equal to 4x1 plus 2x2. So subject to constant minus x1 minus x2 less than or equal to minus x3. So x1 minus x2 less than or equal to 2. Where x1 x2 greater than or equal to 0. Greater than or equal to 0. Uh, Now the dual of the above LPP is minimize W equal to minus 3W1 plus 2W2 subject to minus W1 plus W2 greater than or equal to 4 minus W1 minus W2 greater than or equal to 2 when W1 W2 greater than or equal to 0 greater than or equal to 0. So what we discussed today again once again we'll revise unit 7. Unit 7, primal and dual, a linear programming problem. So, introduction. So, in the previous chapter, we learned several techniques and methods to solve a given LPP linear programming problem. The original, the original linear programming problem, which is given, is called primal. Which is given is called primal. Every LPP which is given is hmm, called primal. Every LPP is associated. Every LPP is associated to a uniquely related another LPP involving the same data. Involving the same data as as described in the original LPP. The original LPP is known as a primal, but the same LPP can be solved by taking the transpose by writing rows into columns of the given statement of one LPP. If written in a matrix form, we get a new LPP without changing the data. This newly formed LPP is called dual of the primal problem. If the primal is a maximization problem, then its dual will be minimization problem, and vice versa. Hmm? And vice versa. So significance of dual of an LPP with illustration. Let's consider let's consider a diet problem as described here. Vitamin B and vitamin C are present in two different foods, namely F1 and F2. F1 and F2. One unit uh, of uh, food, 1 unit of food. F1 contains 3 units of vitamin B and 2 units of vitamin C. Similarly, 1 unit of food. F2 contains 2 units of vitamin B and 2 units of vitamin C in it. A client requirement is 30 units. Of vitamin B and 20 units of vitamin C. Also, 1 unit of uh, food F1 costs 20 and one unit of food F2 costs 25 rupees. Now the problem is that for the hospitals, we to find have to find such foods F1 and F2, which are to be supplied to clients at low price. Means minimum cost. Minimum cost. Minimum cost. So vitamins needed, vitamin B and vitamin C are cost. So food F1, 3 units and vitamin C 2 units. The total cost is 50, 20 rupees. 20. Yeah, food to F2. Vitamin B 2 units, vitamin C 2 units. Total cost is 25 rupees. Here requirements. Here between requirements 30 units, 20 units. So here now we try to understand this problem in detail with reference to primal and real LPPs. If we are the problem from clients 3 aside, the cost is to be minimized. In other words, the food F1 and F2, which contain vitamin B and vitamin C, are to be supplied at lower prices. Lower prices. At the same time, the client is supposed to an intake of at least 30 units of vitamin B from F2 and F3 altogether. Similarly, she is supposed to an intake of at least 20 units of vitamin C from F and F3. Vitamin requirements constraints. So thus the problem aims at minimization of cost, a function subject to vitamin requirements uh, from F1 and F2 called food constraints. This problem is called primal LPP. This problem is called primal LPP. Okay. Now, without any change in the data for the same diet problem, we have another another perspective that is also an LPP, in which the supplier wishes to earn maximum profit by supplying foods F1 and F2 that contain vitamin B and vitamin C from the supplier point of view. If we see this problem, it is quite natural that supplier wishes to make profit from his or her become by supplying F1 and F2 clients, patients through hospitals. In other words, the sum of costs of foods should not exceed the prices of the vitamin subject to provide vitamin to the maximum extent. This leads to the constraints for the supplier. This vary of rating of LPP called dual LPP. So here the entire description can be represented in pictorial form as shown below. So client, so vitamins B and C, hospital, primary, dietary requirement, and food F1 and F2 are profit requirements, food suppliers dual. Thus, we can study this diet problem in two different aspects. One from the uh, client side, primer, and the other from supplier side, dual. So also in primal, the dual is to satisfy the requirement of foods F1 and F2 at a minimum cost. Thus, the cost function is measured equal to 20x1 plus 25x2, where x1, x2 are number of units of F1 and F2, respectively. Uh, in dual problem, the goal is to attain maximum profit to the supplier. Thus, the objective function is maximum Z equal to 30y1 plus 20y2. Here, y1, y2 are the prices of foods F1 and F2, respectively, which are non-negative. Therefore, the dual of any optimization problem will have a good interpretation. Good interpretation. Formation of dual linear programming problem. Dual linear programming problem formation. That the given LPP means linear programming problem uh, is in the form maximize ZX that equal to C1 X1 uh, plus C2 X2 plus so on CN Xn subject to constraints A11 X1 plus A12 X2 plus so on A11 Xn is n less than or equal to B1. Hmm? So A21 X1 plus A22 X2 plus A23 X3 plus so on A2n Xn less than or equal to B2. And so on AM1 X1 plus AM X2 plus AM3 X3 plus so on AM Xn less than or equal to Bn, where X1 comma X2 etc. Xn greater than or equal to 0. Here, hmm, here can be represented in a matrix formation. Matrix maximize Z equal to Cx subject Ax less than or equal to B and X is greater than or equal to 0. B transpose belongs to R power n. R power n. Here A equal to A12, A11, A12, etc. A1n, A21, A22, etc. to n. So on AN1, N2, etc. AMN. Hmm? X equal to capital X equal to X1, X2, etc. So on Xn. B equal to B1, B2, etc. Bn. Bn. So important uh, points in formation of real of primal problem. First one, in a primal problem, if there are n variables, if there are n variables, if there are n variables, if there are in problem there are n variables, m constraints, then its dual problem will have m variables and n constraints. Uh, so if the primal has less than or equal to type of constants, it will become greater than or equal greater than or equal greater than or equal uh, to type of constants and vice versa. Vice versa means if less than or equal to in primal problem less than or equal to is there, it becomes greater than or equal to. Suppose greater than or equal to is there in primal. In dual less than or equal to vice versa means right. Next second one. If the primal has less than or equal to type of constraints, it will become greater than or equal to type of constants and vice versa. So if the primal has third one, if the primal has its primal has its objective function as maximization function, then the dual has in objective function uh, as minimum function, minimization function. What is that? If the primal has an objective function as maximization function, then the dual has its objective function as minimization. Uh, so next one. Okay. The cost of objective function in a primal problem will become as uh, constraints the in the dual problem, and the constants of the primal problem will become costs of the objective function in a dual problem. The decision variables in both the primal and dual are non-negative, means all positive numbers. All are must be positive numbers. So, thus, the dual of the above primal problem in one can be denoted by minimization. B1 yj plus B2 y2 plus Bm ym subject to A11 y1, A21 y2 plus etc. A1 y1 greater than or equal to C1, A12 y1, A22 y2 plus so on, AM2 y2 greater than or equal to C2, etc. A1n y1, A2n y2 plus ym greater than or equal to Cn, a greater than or equal to 1 to m. In general, we denote the above phenomena as primal. Primal means suppose minimum Zx j equal to 1 to n Cj Cj cross j such that j equal to 1 to n aij xj less than or equal to bi j equal to 1 to etc. xj greater than or equal to j equal to 1 to n minimum z by in dual what will happen minimum z by equal to j equal to 1 to n bi by j such that j equal to 1 to n ai j by j less than or equal to ci j equal to 1 to n and y j equal greater than or equal to 0 I equal to 1. Some standard theorems and remarks. Theorem. The dual of the dual of a primal problem is the primal proof. Consider the primal problem in the canonical form minimum z cx subject to constraints ax is greater than or equal to b, comma x greater than or equal to 0, where a is m cross n quotient matrix and b transpose belongs to epsilon power m theta. C x transpose equal belongs to um, belongs to epsilon power n. On applying the rules of the dual problem, we get max zy equal to b transpose y subject to a transpose y less than or equal to c transpose y is greater than or equal to 0. Let us express the primal in standard form. Z by star minus b whole transpose y subject to minus a transpose y greater than or equal to minus c transpose and y is greater than or equal to 0. Where Z by star. Now the dual of the above expression max equal to minus c transpose whole transpose z equal to minus cx subject to minus a transpose whole transpose x less than or equal to minus b transpose whole transpose. That is a x greater than or equal to b, which is primal. Which is primal. Remark: if the ith constant in the primal problem has equality sign, ith dual variable is unrestricted sign. If either the primal problem, or the dual problem has an unbounded solution, uh, then other problem has no feasible solution. So, fundamental theorem on duality. If the primal or the dual has finite optimum solution, then the other problem, dual, will also possess a finite optimum solution and the optimum value of the objective function of either problem or same. So, we completed today unit which is important. So I'm leaving. Thank you very much, dear students.